I'd like to start by saying a big thank you to the organizers of the Arize Observe Summit. This is a really cool event, and I'm so excited to be here. Thank you for including me. Hi, I'm Carey, and today I'm going to be talking about best practices of effective ML teams. So first, a bold claim. Getting a model into production is a solved problem. Coordinating efforts on ML teams is not. And to back that up, I'll tell you a bit about my background, some challenges we've seen in the real world, and solutions. So first, at Weights and Biases, we're building developer tools for machine learning practitioners. And we work directly with these experts every day to understand their pain points. So that includes things like going into the OpenAI office to talk to Peter Welander. He's the team lead for the robotics team. And in this photo, we're talking about a dashboard that they had up on their wall. And we had no idea they were putting our product up in their office. And this kind of learning, directly observing how ML teams are working day to day, allows us to build better tools. And we're able to do that across industries. So I'll touch on 3 case studies, but we have a whole range of customers across different industries. And it's clear every industry is starting to build machine learning teams. So this is a diagram from a few years ago by Siobhan Zillis. And the most recent one I could find, it's actually so large I can't read it. It's amazing to see how fast these things are developing. So everyone's setting up an ML team, but how does that differ from a traditional software team? Well, there are tools for every stage of software development, and it's pretty clear what that workflow looks like. But for machine learning development, it's not as clear. There aren't standards that we all agree on. For the ML workflow, that's data curation, collecting and labeling data, exploring, cleaning it, preparing and transforming. And then there are results that come out of that process, like the raw data set or the trainable set or evaluation set. Next is modeling. So training a new model, evaluating and optimizing it. And then there's a whole host of different artifacts and metadata that might be useful to track during that process. And then we've got deployment. So that's packaging up a model and making it production ready, and then serving and monitoring that model. That also has its own pieces of metadata and artifacts that would be useful to track, like the model predictions. So this process is incredibly cyclical. Once you have a model in development and it's deployed into production, you are monitoring that model's performance, identifying if there are any issues or regressions, and then going back through the flow of either capturing new data, pre-processing it in a different way, maybe finding a new model architecture or better hyperparameters, and constantly iterating on that process. And so this is what I will be touching on in the next 2 sections. So have this in the back of your head. Next up, I'm going to talk about challenges. What are the common pain points and frustrations for ML teams who are working on models day to day? First, I think untracked processes are brittle, but we haven't, as an industry, accepted that that's true for ML models yet. It's still not obvious that people should be version controlling their models. And it really reminds me of this Stack Overflow post from like 10 years ago, where this person asked, why should I use version control? And quoted a blog that said, code doesn't exist unless it's checked into a version control system. I think that's hilarious. That's so true. You know, for models, they don't really exist unless they're tracked. And that isn't necessarily the common opinion. This person goes on to say, if I'm not having other people work on the code and I'm not planning on letting anyone else work on it, why do I need to version control it, right? Thinking of Git or another tool as a collaboration platform. And we're in a really similar spot with machine learning, where it's not obvious that you need to track your workflow if you're not collaborating on a project. But I'd like to challenge this assumption. So looking back at the ML workflow diagram for a second, this area down here with the raw artifacts and metadata that we might care about, this is the stuff that's really critical to track if you want to understand where a model that's deployed to production came from. And this area down here We'll hear echoes of this in the case studies I'm about to share with you. First case study is from the team at OpenAI. I mentioned Peter Welander a couple of slides ago. So he is the team leader there, and they were working on a project called Dactyl, which I think is a really clever name. They're training a robotic hand to solve a Rubik's Cube. And it's doing it one-handed too, which I think is especially impressive. So this is already a hard task for a human to do, to manipulate a Rubik's Cube and solve it with one hand. And they're training a robotic hand to do that in this project. They started with a simplified version of the problem, where it's not a Rubik's Cube, it's a standard cube. They had a hand manipulating that cube so they could start to get some data. And it was clear that this problem still required a lot of coordination. Even though it was simpler than the ultimate goal of the Rubik's Cube, the hand often ended up dropping the cube. And this was all part of the process of iterative experimentation. And so as they're training these reinforcement learning models to perform in this scenario, they attack the problem from multiple different angles. So actually a lot of different ML practitioners were building models at the same time on the team. All of this was happening in parallel, and the results that they were getting ended up being, on each person's laptop or in their own system. So when they were trying to identify training bottlenecks, like did they need more data or more GPUs, more parallel workers to train the jobs, or did they need a different algorithm or different hyperparameters? It wasn't obvious what the next step was because they didn't have a single place to look at all of the results. The results from individual model training was scattered across different places. Like some model files were in S3 buckets. There's the training results, maybe in a TensorBoard file or some screenshots of TensorBoard. There's lots of loose information. And so communicating results ended up being really challenging. That capturing and comparing across people and even across model versions was frustrating. Things like screenshots of TensorBoard, screenshots of the terminal or text files in this case to show what happened for a given model version. And they had a lot of questions. I think a particularly heinous example of this was they were hosting TensorBoard on a remote machine and took a look at that, took a couple of screenshots, and a team member posted that result in Slack. A couple of days later, someone commented and said, "Yeah, I see your loss or your accuracy. Can you show me the validation accuracy?" And at that point, that TensorBoard file was long gone. The instance was blown away. Those kind of questions, the only way to answer them is to actually rerun the training process, retrain the model, and burn that expensive GPU to get those results back. That process was really frustrating for them. And that goes back to our diagram where these important pieces of metadata, context, artifacts that come out of the model training process, those were getting lost because there wasn't a clear place to save them. And that didn't happen automatically. So to summarize their key pain points, they needed help in these three areas. Collaboration, having a tool that lets them share their results and comment on each other's work. Standardization, having everyone tracking results in the same format rather than random text files or spreadsheets or Google Docs. And then reproducibility, taking a given model that someone else trained that's maybe performing well in a given scenario and trying to extend it to your own scenario. That ended up being really tough for them because they didn't have enough context about the given model that they were working on to be able to fully reproduce it. They didn't have, say, the exact version of the data or the exact version of the different packages that were installed when training that model. So having that complete context was really critical and was a missing piece for OpenAI. So next up, I'm going to talk about Blue River and their See and Spray project. Blue River is a company whose goal is to use machine learning to improve agriculture. This is really cool. Their tagline is optimize every plant, like really awesome to see. And the idea behind Blue River is working with farmers to help them run their farms better using machine learning. In this problem statement, farms operating at a massive scale need to kill weeds fast. Here's a actually really cool visualization of what's happening. If you don't kill off the weeds, here on the left, You can see the green crops are growing in the middle, and then the brown, long, stringy weeds are growing between those rows of cotton crop. And you can see the plants are actually kind of stunted. They're smaller and they're not doing as well. And they're not going to produce as much crop because all of the weeds are taking up those vital resources, the water and the nutrients. Over here on the right, you can see a different story. These plants have been sprayed to kill the weeds. And this means that there are actually no weeds that I can see in between those rows of crops. It's just cotton in that field. And that means that the plants are much larger and more developed, and that they'll produce more crop and it'll be higher quality. This, I mean, amazing use case for machine learning. But in particular, what's happening here is really relevant to all of us, which is farmers who are dealing with these massive fields and tons of weeds cropping up between their rows are using Monsanto's Roundup, which is an herbicide, to spray the entire field, and then buying these custom seeds, these GMO crops called Roundup Ready that come from Monsanto as well. And those crops actually survive the spraying. You can spray the whole field, cotton stays, and the weeds die. The reason this is a big deal is there's a lot of agricultural runoff from this process. And that affects all of us. That glyphosate, this herbicide that's being sprayed on the whole field, is just running off in the rain that comes down. So the natural question is, well, why do we have to spray the whole field? Can we maybe just spray the weeds? What would it look like if we only sprayed the weeds? Well, looking at this picture, this is an example of some weeds and crops in a field. I've given this presentation many times. I still have trouble remembering which ones are the crops versus the weeds. So Blue River is working on exactly that problem. They're doing things like semantic segmentation, bounding boxes, building models to identify where the crops in green and the weeds in red. And even seeing them in the bounding boxes, they still look really similar. So this is a hard problem. Blue River is driving tractors through fields with cameras and sensors underneath them to scan the whole field and train their models and then generate predictions of whether or not to spray a given plant. And I like this tagline: see it, spray it, kill it. See and Spray, the project name, this is where that comes from, is looking at every single crop or weed in the field and making a runtime decision whether or not to spray it with the herbicide to kill it. And as you can see, the John Deere logo here, Blue River was acquired by John Deere. That's really exciting. They're able to do this at an even larger scale now. Their goal is to use ML to improve agriculture. And if they only spray the weeds with herbicide, what does that do for runoff? That reduces agricultural runoff from that field by 80%, which is a major deal. It just seems like such an incredible application of ML. So, I mean, it's really been a delight to work with them. And what are the problems they're facing? They need to constantly manage these changing data sets. So they've got folks, team members out in the field, literally with the tractors, looking at different types of crops, lettuce, corn, cotton, and they have to manage not just like the crop type, but also context like time of day or angle of the sun or location. There are a lot of pieces of metadata that go into building their data sets. And that's constantly changing. They're getting new data from the field. They're getting new labels from expert labelers. And this whole process is really complicated. There are a lot of data sets in flight, and they need to be able to track models that were trained on those different conditions, these different versions of the data. And that process is hard because there's a lot of changes that happen during this life cycle that need to be tracked. And it's hard to stay on the same page if you're literally on different fields. So ultimately, what were Blue River's primary challenges? They had trouble tracking data's effect on models and tracing through from data to the ultimate model performance. So how does some change like data pre-processing end up affecting the model downstream? Common questions like, one team member asking another, hey, did you use the latest expert labels that we just got from this new labeling pass to train your model? It's not clear if everyone has access to the latest version of data, if there's no central single place to look for the best data set. And then how do you compare the latest model version to the previous model if you don't have the context of the data it was trained on and you don't have tracked hyperparameter system metrics, all of this? Summarizing that down, Blue River's challenges were really in 3 categories: model lineage, being able to track everything that happened to a model upstream before it's a candidate for production. And then data versioning, tracking the different changes that are being applied to their training data sets. And then data visualization, looking at different scenarios, like how bounding boxes are being predicted by a certain model, and being able to visualize that interactively. Now, I'll go to our last case study here with Toyota. TRI is building safety critical systems because they're doing self-driving cars. So this is a really crucial use case to get right. They're such a fun team to work with because they're exploring these really novel ML techniques. So I'm just so impressed by this approach. They have literally a single camera and they're able to reconstruct a 3D scene. So they don't have LiDAR, they aren't getting point clouds from the sensors. They're constructing that using models. Not only that, they've achieved incredible results with simulation. So training a model in simulation, not on real world data. And the reason this is really cool is it's a lot cheaper. You don't need to have human expert labelers looking at point clouds and labeling point clouds because that information can be generated from the simulation. And simulations are cool, especially for self-driving cars, because you can test your model in scenarios it would never actually see in the real world. Things like a pedestrian jumping in front of the car. You want your car to be rock solid, not flinch when something crazy happens. But it's hard to get that real world data. Simulation is incredibly valuable for this. And I have to say they have amazing results with the results of training a model in simulation. This is pretty complicated. I'll break it down. In the upper left corner, this is a video from a camera on the top of the car. So this is kind of what you would see if you were, say, driving the car on the street. This next piece is the model doing depth prediction. It's color coding farther away as dark purple and closer as yellow. And you can see it's doing a pretty good job because the sky and the distant building is colored dark purple, and then the road that's closer to it is in yellow. This one down here is the semantic segmentation. So that's looking at every pixel from the video and saying, what is this thing? Is this a car or a tree or a sidewalk? And you can see it's doing a pretty good job because the cars are correctly marked in blue. They look good to me. And then over here on the right, this is the coolest in my opinion. This is the model predicting the 3D point cloud of what the scene would look like from just using that flat video in the upper left corner. So it's taking that video as input and generating this point cloud, which is incredible. And you can see that by the colors, it's doing semantic segmentation. So it's predicting what the objects are in the frame in a 3D space. This is incredible, especially because this is representing a transfer of the model being effective in simulation and then seeing real world data and being able to perform well on that real world data. There were no real labels that this model was trained on. That means it never saw an example video from the real world that was marked up like this down here, like semantic segmentation to show it what the ground truth would be. It learned all of this from sim. Just awesome stuff. So what does TRI need in order to operate effectively? Well, their team needs to dig in on example level predictions. So see things like the street view at the top half of this frame and see how the model performed in generating the semantic segmentation masks. So showing where the cars and the people are standing. it's critical to dig in, not just at those high level metrics like MAP, but to actually see these example level predictions in order to understand what the model is doing, where it might have issues. And they need reliable tools to be able to iterate quickly. So this research team at TRI, they're publishing papers constantly. And so they're always operating on the cutting edge. They're coming out with fresh new research, and they need to be able to iterate quickly in order to get there. But they're working on self-driving cars. So they need to have this rock solid foundation. There's no room for error. You can't get it wrong in a self-driving car model. So they need to have these reliable tools to test and track the process that they're running. And that will ultimately allow them to do things like trace back a model lineage once a model's in production and say, here's the manifest of exactly the data, the code, everything that happened before the model made it here. So to summarize what they need, TRI really cares about model tracking and lineage and having that in a single central system. And then they need a tool for data visualization. So to interactively look at predictions and samples and visualize those and then share and comment on them. To summarize this whole section, the common challenges that we're seeing from these customers and the larger group is these three categories: knowledge management, standardization, and technology barriers. So for knowledge management, it's really difficult to track and compare models if you don't have an automated system to do it. And if you can't recreate every pipeline step to reproduce a given model, it's impossible to reliably say how it was created. Teams were frustrated with the tracking and lineage, but also in the slow process of getting results. And so as we were developing our solutions, we had to keep in mind how crucial it is to make reporting live and interactive. Standardization. So there were a lot of ad hoc workflows across the ML team. And that's natural in the context of a Jupyter notebook, like hacking around on a new model. But for something that's destined for production, workflows need to be rock solid. We also saw that when workflows were really ad hoc, that ended up siloing results naturally because people didn't have a standardized system or a shared language to talk about the results they were getting. It also limited visibility into the process of running the ML team. And so someone like an executive or a team leader would have a really hard time understanding how the ML team is operating because there's no visibility into their process. And then technology barriers. They were frustrated with expensive to maintain internal tools. They had other tools that locked them in and they couldn't get their data out. That was frustrating. And then they had difficulty deploying off-the-shelf tools that had high barrier to set up. So what do solutions look like in this space? First is category of reproducibility. A good tool here needs to capture data lineage and provenance, and then capture the whole ML pipeline that leads up to a trained model, having this automatic, reliable system of record. For visualization, dashboards need to be fast and interactive. Collaboration needs to happen in a unified place, a unified shared dashboard. Teams need to have visibility into how projects are going across the team. And then as we were building our tool, we kept in mind the crucial fast integration. It needs to be easy to set up with easy exporting and no lock-in. And it has to be fast to deploy and intuitive to use. So ultimately, we're building towards an ML system of record, something like Salesforce is for sales or Jira is for engineering, this tool that the whole team can use and collaborate on. And it's starting to come to fruition. Here's some quotes from customers. OpenAI has heavily adopted WB into their workflow. It is used as a primary means for sharing results in the team. So that collaboration piece. Blue River says they have full visibility and transparency in the development process, making it easy to identify the most performant models. So that visibility piece. And then Toyota commented, WMB is used as the official record of every ML model that gets built. So that's the standardized central system. When we survey users, they say they love us. Actually, this guy even wrote in an 11 off the scale. So how did we make that happen? We have these 5 key components. We kept the integration lightweight and straightforward, so you only add a couple lines of code. We're also infrastructure agnostic, so you can train on your laptop, on a private cluster, or cloud machines. As long as you have access to the WMB server, you can visualize those results. In terms of tracking, we give you a simple central place to visualize the progress of model training. And we even capture system metrics right out of the box for you. So you can see things like if you're getting low GPU utilization. We also capture the exact code version and any uncommitted changes. And we track artifacts like dataset and model versions. Then we make it easy for you to iterate quickly. So you can use the interactive dashboard to spot issues. You can also compare runs. This allows you to visualize relationships between, say, hyperparameters like learning rate and the metric you care about, like accuracy. And this is all saved in the same standard persistent system of record. So everything you've ever tried is in the same table, and it's easy to query and filter to find the best model or a baseline to compare your new model against. For optimization, we have a tool to scale up training and launch dozens of jobs in parallel to report back to the single central dashboard. And that's critical for having the team be able to move quickly. Finally, we have a big focus on collaboration. Reports allow people to annotate their work and take notes on their progress, and then have a live dashboard where they can describe what they were working on and show charts that will update in real time. It's also possible to comment directly on reports, kind of like a Google Doc with charts in it. And this allows teams to collaborate easily and gives team members access to results that they might not have seen otherwise. So that's a quick summary of our solution. In conclusion, I think the ML workflow is, for a lot of teams, really messy. So weights and biases is building standardized tools to help teams be more effective. In the data realm, that's data versioning, so tracking data lineage and data exploration tools. In the modeling phase, that's experiment tracking, so tracking hyperparameters, the code version, system metrics. And then in the deployment stage, that's the model registry, so tracking production models, making it clear the lineage of a given model, and presenting model cards. And soon we're working on production monitoring. And production monitoring will allow you to track model performance in production and compare it to how it performed during training. In conclusion, effective ML teams have automated tooling to capture their progress. Thank you. This has been a pleasure.